Hey, hello there. Today's Leetcode challenge question is called the cheapest flights within K stops. So it's quite a nice problem. It's quite real life relatable, and it also has a lot of different ways of solving this problem. So yeah, I'm going to talk about two solutions. Yeah, let's see the problem. We have some cities that are connected by some flights. Each flight can be described by three pieces of information: the departure city, the arrival city, and also a price of the flight. So if we treat the city as nodes in a graph, it's going to be a directed graph. The edge is going to be the flights, and the edges also have a weight. The weight is the price of the flight. So given the cities and flights up front, so we have the full information about the graph. What we want to do is to answer queries like this: a starting city and a destination city. We want to find the cheapest price from the source to the destination with up to k stops. So we're looking for a path inside this graph from the source node to the destination node with at most the k intermediate node along the path. So we're looking for passes that has length, the number of nodes that's maximum to be k equal to 2, or looking at the path with at most the k plus 1 edges. For all those passes that satisfy this requirement, we're looking for the cheapest one. The cheap means the sum of all the weights on the edge. So we're looking for the cheapest. So it's more like an optimization question rather than a shortest path finding problem. So I think that's quite important to keep in mind. I don't think we want to go through this toy examples. Let's just think about how we're gonna do this, flight finding as a normal human being. So just take my example. I was trying to buy a ticket for my in-law to fly from Boston to Shanghai, go back to China. So the first flight we look at is the direct flight from Boston to Shanghai. There used to be one, but it's no longer available. So the price for that is effectively infinity. So that's k equal to 0 is no luck. So what do we end up? So the logical next step is to consider some connection flight. So we look at from Boston to cities like New York, Detroit, Los Angeles, and then from that city we fly back to Shanghai. There are some flights being sold, but the price is ridiculous, and also there were the uncertainty. I think there's still the uncertainty whether the U.S. flights can directly fly from city in the U.S. to China. So and also the price is just too high. So we end up relaxing the k to consider one more intermediate stop. That's a city in South Korea. So we're gonna from Boston to Detroit, from Detroit to I forgot the name of the city in South Korea, and then from there to Shanghai. So it's within our tolerance of the k, and the price is reasonable. It's lower than from Boston to Los Angeles, from Los Angeles to Shanghai. It's lower than from Boston directly to China. That's effectively infinity for that case. So it's sort of like this procedure as I described here. It's if you try to implement this strategy to solve this problem, it will work. How you actually implement this is going to determine how effective this is going to be. So the most straightforward way of doing that is like a Bfs search. We'll look at the first immediately connection. Do we have that one? If we do have them, we note down the price for that, and then we do another round to include with one intermediate flight. So the path of 3 nodes, two flights, and see how much that's gonna be from the source to the destination in that way. So it's a level by level Bfs search, and we're gonna keep a running minimum and just keep updating that. One thing that's quite important in this Bfs approach is going to be try to prune the tree. So let's say that if we fly from Boston to Shanghai, if the usual flight is still available and the price is as the usual level, it's going to be around $600 or something. But if now a flight from Boston to Los Angeles costs more than 600, no matter how the price in the second part from Los Angeles to Shanghai is going to be looking like, we're not going to consider that as the possibility. So doing the BFS search, we're going to try to aggressively prune it if the partial pass it's more expensive than the no minimum right now. So that's going to be the really key important part if we want to implement this search strategy with BFS search. So let's code the BFS search. One thing we need to do is to do the graph processing. What we have here is the sort of like an edge list. We want to convert that into the adjacency list. So we're going to have the source node. I'm going to use a hash map. The source node is going to be the key. The pair of target node and the price, the weight on the edge, are going to be the value on a list for that. So it's going to be a hash map with integer to list of pairs. So that's going to be the adjacency list, and we're going to use a queue to implement the BFS search. So let's do the graph processing. Let's define this infinity here first. So graph processing. My brain power is low today, so bear with me. For you, the departure city, arrival city, and the price in this flights, this is the edge list format. What we're going to do is to have the source, the departure city, to be the key, and we append the pair of target city, the destination city, and the price on it. So when we look at where we can go from the source, this source city, we're gonna enumerate over all the pairs on the in the values here, and we have a queue. Initially, it's going to be the stuff on the queue are going to be the partial pass. It's going to be the source and current total for the pass. The first element are going to be the current location. The second element is the price. So initially that's that. The looping condition is gonna be while we still have this queue here, which is not empty, and k plus 2. We're gonna decrement k every iteration here. The reason for it being k, we're gonna run this for k plus 2 times is that we considered k plus 2 cities at most. We have k cities that's in between, and we have the source and the target, the destination on both ends. So the looping is going to be k plus 2. So every iteration we're going to do level-wise. So we're going to examine all the paths we have on this level. So this for loop makes sure that we'll visit all the partial paths we have on this level. We're gonna pop this pair of information out. It's the location and the total, partial total. It's gonna be popping this pair of information out of the queue. And if this location is equal to the destination, we will try to update no minimum price. Initially this is infinity. and just code up the return here very quickly. Oh, sorry. So that's the return. If we can find a path from source to destination, this minimum price is going to be lower than the default infinity. Otherwise, it will be impossible. In that case, we'll return -1. So in the Bfs search, if we find that the paths actually have this location to be the destination, this is the time we try to update this minimum price. It's going to be total. Otherwise, that means we will try to fly from that location to some other next stop. So we're going to enumerate over all the next location, next city we can try to go. W price. Graph location. One thing that's important is that the pruning I was mentioning. If the partial price for this pass is larger than the no minimum, we're gonna give up on that pass. So that's total plus price larger than the minimum price. We're gonna give up. Otherwise, we will push this pair of information on the queue. Yeah, so that's what that's the code, I think. Let me try. Nope, wrong time arrow. It's a big K. Okay, it's a capital K. Right? Let me see. Yeah, it's working. Okay. Yeah, so this is the BFS code. Let's see how the time complexity works. It's not going to be great. So the graph process here is the number of edges in time and space. What we did is to convert the edge list into adjacency list. So that's how many edges we have, how much time and space we use for that. Then there's this Bfs search. Note that here, let's just see this. In the beginning, the queue only have one source city, and for all the city that's visitable from this source, we're gonna put all of those cities onto the queue. So after this very first for loop, we can potentially have a number of cities, number of nodes on the queue. And in the second iteration, for all those cities, if everything is interconnected with each other, for every city, it's gonna be bringing another number of nodes. So it's gonna be v to the power of something. So it's gonna roughly be v to the k. So that's the time complexity and also the space. So it's quite bad in the time and space if we look at the loose upper bound. But the thing here is that as long as there are some direction, if there are direct flights that's available, or some very small k paths that's early on available to us, the pruning is gonna kick in. Once the pruning is has kicked in, the runtime will be much better. So it's not really that bad. So that's that. That's the Bfs search. So the other way of solving this, because we, as I earlier, when I pointed out that it's more a optimization problem by finding the cheapest, we can use the typical strategy like a dynamic programming to solve this problem. We're going to look at how the dynamic programming is going to be doing. It's still going to be similar to the procedure I described, looking at the direct flights, looking at the flights with one intermediate stop, looking at the flights with two intermediate stop, things like that. The thing that the dynamic programming can address is the situation like here, the BFS wouldn't be able to handle. The duplication happens inside here, because let's say that if we visit Shanghai is now our target. We are from Boston. We know that in the very first Bfs search, we know that flying to New York is going to cost maybe like $200, and the flight to Detroit is going to cost $150 or something. And then in the second Bfs search level, we find that the Detroit to New York is going to cost another 150 or 200. So the BFS will still have the pass from Boston to Detroit, from Detroit to New York. But we know in the first level of Bfs search, from Boston to New York, it's 200. So the other pass that containing Detroit as the intermediate connection to New York, it's more expensive than the flight from Boston to New York and from New York to whatever the next destination. The Bfs search will not get rid of those kind of stupid considerations, but for dynamic programming we can do that. So let's just think about this in a top-down kind of fashion, in a more formulaic way. Let's say that we now taking k flights. So let's just use some generic number I and j. So let's define this. It's going to be the price to fly to city J with I flight. So this is the definition for this, the cheapest price. So effectively what this question is asking us is to return k plus 1. We're looking at k plus 1 different flights, and the city is going to be DST. We'll put a source here. So the question is asking this. What's the relationship, the recursive relationship we can have? What's the subprogram we can set it up? This is going to be fi minus 1j. So if we can fly, it's going to be, if we can fly to, it's possible if the direct flight or flight with less stop, it's cheaper than some other kind of options we will have. We will definitely still keep this as one of the options. It's going to be the minimum between with no additional intermediate flight compared to actually take one intermediate flight. That's going to be fi minus 1 and some other city. Let's say that's k plus the price to fly from K to J. For all K that's viable. So it's going to be the minimum between this. So the first term here, when we consider all, is going to be all the flight that's first from source to the city K, and then from K to J, to our true destination. And the other option is to take one less intermediate flight and directly from the source to the true target J. So this value is going to be the minimum between these two things. So that's going to be the transition function. And the base case is going to be f0. If we don't take any flight, we're stuck at the source. So that's going to be j equal to infinity if j is not the source. Otherwise, it will be 0. If we're already at the source, it's going to be 0. That's the first. That's the base case. And what else? F1j. It's basically going to be the edges we actually had. So yeah, that's normal. We will be able to populate that out. Yeah, because effectively everything here is going to be in the first term. It's going to be infinity, and only the no. Let's populate this. F1j is going to be minimum between F0k plus, okay, yeah. So the second term is going to be infinity because Fi0j for all the j that's not to the source, it's going to be infinity. The first one is going to be from 0 to source. That one is 0 plus the price from source to j. So the only true base case is this one. So that's the base case. Yeah, so with this, we should be able to figure out the dynamic programming code. We can either do top-down or bottom-up, but we can do bottom-up. Note that in this relationship, what we have is the dependence of I with I minus 1. So if we have this 2D table where the I is the rows, j is the columns, we can compress this into just one or two row, so that we can have a space optimized solution. But my brain power is really low, so I think I'm gonna just code the 2D to use this I relationship. All right, so that's pretty much the DP. Note that the difference between this DP and this Bfs search is the thing that I described. If we know the price that it costs to fly from Boston to New York, and we direct flight, we will never consider anything that's anything like a flight to Detroit and then from Detroit to New York, when the price for flying to Detroit to New York is larger than directly flying to New York. If New York is not our destination, so it works like treating basically it's just much better compared to this Bfs search. This does not do that kind of pruning, optimization, I would say. So yeah, let's code the DP solution. I don't know what I'm talking about. Anyway, so we're gonna have a two-dimensional DP table. We're gonna have the k plus 1. That's gonna be the rows. K plus 2 from 0 to k plus 1. The base case is that everything is infinity except for that. We're gonna populate that. K plus 2 DPI SRC is going to be 0. Yeah, I think I should also mention one more base case. F K plus F whatever SRC is going to be 0. If we are at source, it's always free to go to this source location. So yeah, so that's that. Then we do this using this transition function to populate this. I'm gonna throw a loop I in range 1 to k plus 2. So so it's a minimum between a collection of things and one item. So we can move the 4 outside and just take the minimum between 2 items. So that's equivalent, and it's easier to code. For UVW in flights, we are taking DP I and J, which is going to be I and V here. It's going to be the minimum between this and what? dp I minus 1 u plus w. So this is the price from the source to city V with I flights. It's going to be minimum between. We try to update this value with try to see if it makes sense to take one more connection. How do we populate? How do we move this value over here? So I need to move the I minus 1 j value to the ij value. So let's just so dpi equal to dpi minus 1, would that work? And then it's basically just taking the minimum between these two one at a time, moving the for loop out and do the minimum inside that. Yeah, it seems so. So what we need to return is the very last row in the DP table with the destination city. Look up at that value. Looks like the code. Very short actually. Let's see if it works. Nope, runtime error. What's the problem? Indexed out of range for I minus 1 u plus w to. What's the problem? Oh, the I is out of range. I'm looking at only. It's a stupid mistake. That's the number of columns. Yeah. So this should still be k plus 2. Sure. This is not right. The second item should be 500. What do I have on my DP table? From 0 to 1 is 100. From 0 to 2 is 200. That's the beginning. There's no way. So I shouldn't copy this. Why? I might mistaken this. This should be just taking the minimum among all of those. Did I mess up the recursive relationship? Does this look like? 0, infinity, infinity, that makes sense. 100, 500, 100, 200. What about if I change the second case to be instead of flight to 2, I'm only interested in flight to 1. That works too. Anyway, I'll figure out what I have wrong and drop a comments down there. It seems that I'm not really should do the minimum between the connection flights with the given number on the connection flight. That's how the code looks like right now. Why is that? Yeah, I will figure out and leave a comments. Just couldn't think anymore right now. Can it be accepted? Yes, it is. Yeah, I will leave a comments. What's the problem? Yeah, before that, I think I can at least do some runtime analysis. It's funny that no idea why the code works. So this outer loop is out of k, obviously, and this inner loop here is out of number of flights, the number of edges. So it's a multiple of e plus k. So that's the total runtime. Right? Yes, it's a 4 and 4 nested for loop. The outer loop is k, the inner loop is number of edges. And for space, it's a two-dimensional DP. It's the number of nodes multiplied by the k. Yeah, so that's the space. It should be much better compared to this one. It's exponential, but with pruning, it's not necessarily that big. Yeah, so that's the question today. I will look up doing some correction later on.